Space wonderful, isn't it? But what if I tell you space always wasn't like this? It started all with the Big Bang. Its initial state about 13.8 billion years ago. In the first fraction of a second, the universe underwent cosmic inflation, expanding exponentially faster than the speed of light, which doesn't violate relativity because space itself was stretching. During this time, tiny quantum fluctuations were stretched to cosmic scales, later becoming the seeds for galaxies. As inflation ended, the universe entered a hot, dense phase filled with a plasma of fundamental particles: quarks, gluons, electrons, and photons. Within microseconds, quarks combined to form protons and neutrons, and within the first few minutes, a process called Big Bang nucleosynthesis produced the first atomic nuclei, primarily hydrogen, helium, and trace amounts of lithium. For the next several 100,000 years, the universe remained an opaque, glowing plasma because electrons could not yet bind to nuclei. Around 380,000 years after the beginning, temperatures dropped enough for electrons to combine with nuclei in an event called recombination, forming neutral atoms and allowing light to travel freely for the first time. This light is observed today as the cosmic microwave background radiation, a nearly uniform glow detected in all directions that provides a snapshot of the early universe. After this dark age, gravity gradually amplified small density variations, leading to the formation of the first stars and galaxies a few 100 million years later. These early stars began fusing heavier elements, enriching the universe and eventually enabling the formation of planets and, much later, life. Observational evidence strongly supports this model. The expansion of the universe, first quantified by Edwin Hubble, shows that distant galaxies are moving away from us, with farther ones receding faster. Additionally, precise measurements of the cosmic microwave background, especially by missions like Planck's satellite, reveal tiny temperature fluctuations that match predictions of inflation and structure formation. Together with the observed abundance of light elements, these findings make the Big Bang the most robust and widely accepted explanation for the origin and evolution of the universe. After a galaxy was born, its evolution became a long and complex process shaped by both internal activity and external interactions. Vast clouds of gas within the galaxy continued collapsing under gravity, forming new stars in regions often called stellar nurseries. These stars lived for millions to billions of years, depending on their size, and the most massive ones ended their lives in dramatic supernova explosions. Such explosions were crucial because they created and scattered heavy elements, like iron, carbon, and oxygen, enriching the galaxy and allowing later generations of stars to form planets and complex chemistry. Meanwhile, many galaxies experienced collisions and mergers with nearby galaxies, which could distort their shapes, turn spiral galaxies into elliptical ones, and trigger intense bursts of star formation known as starbursts. At their centers, most galaxies developed supermassive black holes that could grow by pulling in surrounding matter, sometimes releasing enormous energy as quasars. Over time, as gas supplies were used up or blown away by stellar winds and black hole activity, star formation slowed, causing galaxies to age and become more stable. Even today, galaxies continue to evolve, showing that the universe remains active and ever-changing billions of years after their formation. After galaxies and stars formed, the universe entered a richly dynamic period shaped by gravity, nuclear physics, and long-term cosmic expansion. Inside galaxies, stars began forming in dense clouds of gas and dust, igniting nuclear fusion in their cores. Massive stars burned quickly and ended their lives in powerful supernova explosions, while smaller stars evolved more slowly, eventually becoming white dwarfs. These stellar deaths were crucial. They forged and scattered heavy elements into space, enriching the surrounding interstellar medium. Over time, this recycled material gave rise to new generations of stars and increasingly complex planetary systems. In some regions, protoplanetary disks formed around young stars, where dust grains stuck together, gradually building planets, moons, and asteroids. As galaxies evolved, they often interacted and merged with one another, reshaping their structures and triggering bursts of star formation. Supermassive black holes grew at the centers of most galaxies, sometimes becoming active and releasing enormous energy as quasars. On even larger scales, galaxies assembled into clusters and vast filaments, separated by enormous voids, forming what scientists call the cosmic web. Meanwhile, the expansion of the universe, driven in part by what we describe as dark energy, continued to accelerate, causing distant galaxies to move farther apart over time. Star formation rates, once much higher in the early universe, gradually declined as galaxies used up or lost much of their cold gas. Billions of years later, this led to a quieter universe with fewer new stars being born. Looking far into the future, astronomers predict that star formation will eventually cease almost entirely, leaving behind long-lived stellar remnants, cold gas and dark, aging objects. The universe will continue expanding and cooling, moving toward a state where energy is more evenly spread out and less capable of sustaining complex processes, sometimes referred to as the heat death scenario. Despite this gradual fading on a cosmic scale, the processes set in motion after the first stars formed ultimately made possible the emergence of planets, chemistry, and life in certain corners of the universe. Prehistoric life refers to the vast span of time before written records, when Earth was inhabited by a wide variety of ancient organisms. It began with simple single-celled life forms in the oceans over 3.5 billion years ago and gradually evolved into more complex plants and animals. During different eras such as the Paleozoic, Mesozoic, and Cenozoic, life diversified dramatically. The Mesozoic era is especially well known for the dominance of dinosaurs, alongside early mammals and birds. Prehistoric life also includes giant marine reptiles, massive insects, and early human ancestors. Fossils provide scientists with important clues about how these organisms lived, adapted, and evolved over millions of years, helping us understand the history of life on Earth. Subscribe and share and like to support me, and I will see you later.